This is Edexcel A-Level Further Maths 2021 Pure Core Paper 1. I'm not going to work through every question. I'm going to make this deliberately a quick video, but I wanted to illustrate one technique that I think might be worth trying, which is to invest the first perhaps 15 minutes of the exam getting your bearings and breaking the big problem of an hour and a half exam where you want to get as many of the 75 marks as possible into smaller problems. Plan for what is difficult while it is easy. Do what is great while it is small. Every large task can be broken down into smaller pieces, and it's only by dealing with those smaller pieces that you're going to effectively tackle the entire thing. What I want to do at the beginning is just make some quick notes for myself on every single question. These you can do for yourself on the exam paper as you go. Make some little bullet points at the top. Maybe circle any key things that you think stand out to you and that might be relevant later. So let's jump in. The first question, I'm going to jot down what immediately springs to mind as I read it. So I've got a transformation matrix. I'm going to make a note to myself to check the formula book. Maybe I turn to that particular page so that I can link in my head things like the rotation matrices and the reflection matrices. Because I suspect the matrix they're giving me is going to be some combination of those. I also need to make a note, perhaps, as I read through, it looks like it describes an enlargement and a rotation. The order is going to make a difference. Transformation P followed by transformation Q. I've got to remember that matrices behave like functions. So PQ means Q then P, and QP means P then Q. I can see this because if we apply Q and P to a vector V, then effectively this is equivalent to applying the vector P, applying the matrix P to vector V, and then applying the matrix Q to the result of applying P to V. So keeping track of what that represents is going to be useful for me. It tells me I need to find the value of K and the smallest value of theta. So I'm definitely going to need the rotation matrix for this rotation that they're describing for the transformation Q, and the enlargement that they describe. I can make a matrix of that as well. So I might jot down for myself before I move on and before I look at the next bit of the question, what an enlargement matrix might look like. So typically an enlargement is just going to be something along the lines of, if it's a straightforward enlargement, center of the origin, scale factor K, I think it's going to be something like this. It looks like the identity matrix, but with both of these bits stretched by scale factor K in the X direction and in the Y direction. Now the later bits of this seem to be talking about transforming a square. I'm going to get to that when I get to that, but I have a sense now of what that question involves, and I'm going to move on to the second question. This one involves Maclaurin. Straight away, as soon as I see that, I'm thinking, let's look at the formula book. It will tell me the series, some of which are valid for all values of x, but some of which we need to watch out for. So just be aware of and keep an eye out for that. It says we can make use of the expansion for cos to determine the expansion for cos squared of x over 3. So we're going to need to do some combination of things. We need terms up to x to the 4. We could square cos of x over 3, or the expansion of cos of x over 3. Without too much work. I happen to remember that the expansions for sine and cos have alternating powers of x. So the cos one is going to have only odd powers of x, and that means that there won't be that many terms up to the term in x to the 4. There'll be a constant and there'll be an x cubed term, and that's it. So I don't think that that's going to be too much work. Using your answer to part A and calculus, find an approximation to 5 decimal places for this. Now, it's not immediately obvious why we're looking for an approximation, but when you think about the fact that they've just told you to use part A, hopefully it becomes clear. We found an approximation for cos squared of x over 3, and this integral is going to be potentially a bit of a messy one to do exactly. So by replacing cos squared of x over 3 with the Maclaurin series expansion, hopefully that will give us something that's easier to integrate. It's going to give me an approximation, but it should be close-ish to the real thing, provided x is small. And between pi by 6 and pi by 2 is small enough that it should give me some reasonably good approximations. It does say to 5 decimal places. I'm going to make a note of that as well. It's the kind of little detail that doesn't matter until the end of a question, but at the end, you don't want to lose one of your 3 marks for not noticing what you're supposed to round to. Use the integration function on your calculator for the next bit. That's really quick. I could even do that straight away if I wanted to. Before I get distracted or bogged down, it's a 1 marker and I can crank it out straight away if I decide to. I can put it up on here. I'm not going to do that right now, but it's certainly something you could try if you wanted to get 1 mark in straight away. Then you'd have a number. You'd know when you work this out that your number was likely to be correct. Assuming part C is correct to 5 decimal places, comment on the accuracy. Well, hopefully the 2 numbers will not be wildly different. Otherwise, that would suggest to me that my approximation was wrong. But they're also unlikely to be massively similar because pi by 2 is quite a large number. It's 1.5 something. So the cos series expansion is going to be starting to get less and less accurate as x gets bigger and bigger. We're getting further from the center of the expansion. Remember, Maclaurin series, as opposed to a Taylor series that can be centered anywhere, Maclaurin series is always centered at the origin. So that's something to think about. Likely to be a decent approximation, but not superb, because pi by 2 isn't especially close to 0. But I think it would be unlikely for them to give you something where it was wildly off, because that would make it harder for you to tell that you've done the right thing. Question 3. The obligatory roots of polynomials question. So I might start by doing myself a favor and writing down the standard results that I might rely on throughout this question. The sum of alpha, the sum of alpha beta, so the sum of the roots, the sum of the pairs, and this is a cubic, so the sum of the triplets is equivalent to just the product of the 3 roots. And writing them down at the beginning means hopefully I'm less likely to make sign errors when I come to do this question later on. They give me a different cubic equation. This one looks like all of the roots are a nice linear combination of the other ones. One thing you can do instead of using VAT's results is to say to yourself, well, what happens if x is equal to 4 alpha minus 1? Rearrange for alpha, we should get x plus 1 over 4, and that tells me something useful. I already know that f of alpha is 0. If alpha is a root of f of x, I'm assuming that ax cubed add bx squared minus 19x minus b is f of x for the sake of this demonstration. And that means that I would like g, the new function that I'm trying to create, I need g of 4 alpha minus 1 to be 0. How do I make that 0? Well, I need to work out what g is in relation to f. And I want g of x, so that's going to be related to f of x plus 1 over 4. You can check that by saying to yourself, what happens if in place of x I put 4 alpha minus 1? Well, if g of x is equal to f of x at 1 over 4, then g of 4 alpha minus 1 will be f of 4 alpha minus 1 plus 1, that's 4 alpha, divided by 4, that's alpha, and f of alpha is 0. In other words, 4 alpha minus 1 will be a root of this new function, provided the new function is created from the old function here. I'm going to add one tip to myself to remember. X add 1 over 4. I'm likely to have to square it, cube it, do various things with it. So I'm going to remind myself before I get too far into it but I don't necessarily have to cube something messy with fractions. I can pull the fraction out, 1 over 4 to the power of 3, and then I'm just left with an x sub 1 cubed, which I can expand in my sleep. Let's look at the next question. This one involves matrices, but we've got a 2 by 2 and a 2 by 3. And the first bit is an explain, so we can think about just the row times column times row times column. Think about the process you follow when you multiply matrices. The fact that as you move along the rows of one and down the columns of the other one, you need the corresponding lengths to be the same. So we need the let's see what's the easiest way to demonstrate this. If we have a 2 by 2 matrix, that means 2 rows, 2 columns. A 2 by 3 matrix means 2 rows and 3 columns. Around. Explain whether it is possible to evaluate this first one multiplied by this second one. Well, you could just try doing it for yourself and think, what happens if I do this number times this, and this number times this? Yeah, that seems to work. They work. The row of this one corresponds to the column of this one. This second row corresponds to the every column that we want. So we can do, for instance, this one times this, and then this one times this, and that's going to give us, because it was the first row of the first matrix and the first column of the second, it will give me the first row, first column term in the result. Remember that the final result will correspond to the rows of the first and the columns of the second. You can't, however, add matrices like that because you wouldn't have corresponding terms for each one. This next bit, they've given us 2 3 by 3 matrices, one of which we have all the numbers for. So it's worth thinking the calculator can deal with matrices if we've got numbers involved for all of those. And we're asked to find the values of a whole bunch of unknowns. But they've given us a bit of a clue here that if you were to multiply these two things, you would get some multiple of the identity matrix. So perhaps one thing you could try here is using the fact that there's inverse matrices going on. In fact, if you read down a bit, it says hence deduce the inverse of the matrix. So it looks like the method they want you to use for finding these does not involve the inverse. So probably the most efficient way forward would not be to find the inverse first. But once you've worked out those unknown values, getting an inverse should be doable from that point. If you think about it, the inverse is defined as the matrix which, when you multiply it by another matrix, gives you the identity matrix. So if you were to divide one of these matrices by lambda, then it would, by definition, be the inverse of the other one. So M inverse is equal to I. We can make use of that idea. And then this one looks like some form of transformation, but it says determine the values of theta for which the matrix M is singular. This particular one, when I look a bit more closely, although it has some features of a rotation matrix that you might find in the formula book, it's not exactly the same. There's sine thetas, but also sine 2 thetas. There's 1, 1, 1 all the way along the top. But to find the values of theta for which the matrix is singular, singular means the determinant is 0. That's the one bit of working out the inverse matrix where potentially things could blow up in your face when you divide by the determinant. Let's move on. Look at question 5. Evaluate the improper integral. First of all, it's improper fairly obviously because of the infinity. We have an unbounded integral because the upper limit is undefined. To evaluate it, you would need to set the upper limit to some value t, integrate directly, and make t tend towards infinity. Until we actually get into it, we can't tell exactly what the limits are going to look like, but the integral itself looks quite nice because it's just e to the power of something linear. So we can integrate it using inspection, reverse chain rule, or if you really want, you could do a substitution, u equals minus a half x, and it will come out quite simply. The next bit seems to be a bit of a phase shift. They're then talking about sines and causes. Use calculus to show the mean air temperature on this day is 8 degrees according to the model. The mean air temperature, when it gives you the temperature theta throughout a day between 0 and 24 hours. So the mean air temperature looks like we're looking for the mean value of a function. The definition of that is the integral between a and b of the function, but then that just gives you the total area. If you want the average height, you need to divide the total area by the width of the base. So imagine your curve. Imagine what happens if you're trying to find the average for that function. It's a bit like working out your average speed. You might be speeding up, slowing down, going at different speeds at different times. Your average speed can be calculated always by doing your total distance divided by the total time. And then given that the actual mean temperature was higher than 8, explain how the model could be refined. That's a detail we can get to later. Let's look ahead at question 6. A tourist does a bungee jump from a bridge onto a river. This one is skipping ahead to the differential equation that I can see. We've got second order homogeneous. We're going to check the auxiliary equation. For instance, two real roots will be something like a e to the px plus b e to the qx, where p and q are the real roots. I think traditionally they're known as alpha and beta. We might reserve p and q when we've got complex roots. This particular one, since it's a bungee jump, is likely to be a complex roots one. So if you have complex roots, you'll have something along the lines of, and I should really watch out for these, that's something to be aware of straight away. Something you can see when you're looking from above, from a distance before you jump into a question. What are the variables? This is x in terms of t that we're looking for eventually. That's what your particular solution will look like. So watch out, it's going to be x in terms of t, not y in terms of x. And if you have complex roots, it's going to look something more like e to the pt times a cos qt plus b sine qt. The imaginary bits, remember, can end up rearranging themselves into trigonometry. Particular solution will involve using the additional values they've given us in here, so that might be worth highlighting as you go through that. Let's look at question 7. Question 7 involves plane equations. The first thing I'm going to note to myself is that I could use the cross product to find a normal to this. But they've actually started me out here, if I read ahead, with show that this is perpendicular to the plane. So it might be even quicker to use the dot product. As long as you could justify and show enough working for the cross product, that would be equally valid. Show that the vector they've created here is at least parallel to the cross product you create from these two direction vectors. And if they didn't give you this bit, then it's quite a bit of work to get unless you use the cross product. So it's worth being aware of. Hence, find the Cartesian equation. Remember that if you dot r, which is just x, y, and z, with n, a normal vector, then that's going to give a constant. That constant happens to be the same as a particular point on the plane dotted with the same normal vector. So you pick a point that you know is on the plane, in this case, for instance, 3, 3, 2, and we're nearly there. They've already given us a vector which is normal to the plane. So 2, 3 minus 4, and we're well on the way to having the Cartesian equation for our plane. You've got a bit of a dot product to complete, and then you'd write this out as 2x have 3y minus 4z, and you're nearly done. For the next bit, it talks about the shortest distance between a point on a line and a plane, asks for the possible coordinates of A. So this line and a point on the line, they've told you there is a particular distance between that point and the plane, and they're suggesting there are two different places, or at least two different places from the plural, that A could be. So imagine a line and a plane, and a point on the line that is a particular distance from the plane. Well, unless the line is parallel to the plane, then there's not going to be that many places on the line that are exactly a particular distance from the plane. I suspect two places. Imagine a ray of light shining through the surface of the sea. There's going to be a point on that ray of light that's a meter above the surface, and there'll be another point a meter below the surface. And that's what they're looking for here. For the distance from a point to the plane, you want to be thinking about project a vector from the point to the plane onto the unit normal for the plane. If you project onto the unit normal, then it's going to tell you just how much of that vector you've created is pointing in the direction of the normal. And then you work out the size of that, you've got the distance. Now this is a bit of a working backwards question. We're going to have A in terms of t, and the distance is going to be given for us. So we'll be working out the value for t that corresponds to this particular distance. And the two solutions will probably come from positive or negative square root of something. So that is what I'm aware of right at the beginning before I even get into the question. And question 8. Two different colors of paint are being mixed. This one's going to be one of those questions that really will benefit you to take your time and think through carefully what's happening. But it might be a question that you want to get stuck into early on in the paper, as long as you've got an eye on the time. It's a question that will take a bit of time, but it's absolutely doable, especially since it starts with a show that. So as long as you can create this, it's very nearly exactly what you're looking for. You just need to figure out what alpha would be. So we've got a mixture of 10 litres of red paint, 20 litres of blue, and as paint is poured in, it's stirred instantly. We have red paint added to the container at a constant rate and blue paint added, and mixed paint is removed at a rate of 3 litres per second. So the total amount of paint stays constant. 2 litres and 1 litre goes in, 3 litres comes out. But they're interested in the amount of red paint in the container at any given moment. And for that, you would have to think in terms of concentrations. So the only things I'm going to make a note of here are things like define your variables. State clearly what you're working out. Don't, for instance, write things like volume equals 30, because the volume is going to be something that potentially will change over time. In this particular case, it won't, because they said the same amount is coming in as going out. But in general, anything that might change, make it clear. If you're saying this is the volume at time t equals 0, then put that v0, or when t is 0, v is such and such. And they've obviously got their variable r representing the amount of red paint. You want to think carefully about how you calculate the rate at which that changes by thinking about how much is being added and how much is being taken out. The amount added is going to be basically a litre a second. The amount removed, 3 litres at a concentration to be determined. That concentration corresponds to the amount of red paint currently in there. That's why we end up with a differential equation, because that concentration will involve R. The second bit, solve the differential equation and then use that to evaluate the model. So all of that comes after you've done the grunt work at the beginning. Okay, so that brings us to the final question. Question 9, hyperbolic substitution and calculus. It's always helpful, I think, when they tell you the result you're trying to get to. So although this looks a little scary, it's already told you it should be a hyperbolic substitution, and it's given you the results effectively. This first bit looks like it's going to come out with some relatively ordinary integration. The second bit implies that the substitution you'll need is cosh. If you replace x with cosh u, you're going to get cosh squared u minus 1. We can check the formula book for the hyperbolic identities just to make sure we're doing that right. But cosh squared minus 1 should help us to reduce that to something else. I'm not quite sure until I jump in exactly what's going to come out, but hopefully things will cancel out. It's possible that you need a different one. Thinking about those identities, because of the x squared on the top, it might even be that you need x equals shine u or something else. You'd have to play around with it for yourself. This next bit talks about the sketch of a curve with this equation, and you're using algebraic integration and your result to show that the area is given by this exact result. Well, this corresponds in some way to this. We're looking for the integral of this. We need to look at where it crosses. So we find the root of the curve, and then we're going to look for a link with the first part of the question. So we have something involving x times arc cosh x. This doesn't look identical to x times arc cosh x, but we've got a result here which arguably could be used forwards or backwards. So potentially we've got the makings of integration by parts, perhaps. If we already have a way of integrating arc cosh, we could make use of that potentially. It does say the result from part A, so it implies that at some point we're going to end up with that. I think what will happen is, if we use parts, we can replace arc cosh x with its derivative and x with its integral. Well, the integral of x is x squared. The derivative of arc cosh, which we'll be able to verify in a minute from the formula book if we needed, is probably 1 over the square root of x squared minus 1, or something like that. So I suspect this is what comes up as soon as you integrate by parts. And then the only thing you've got to be careful of is keeping your values precise. I believe the formula book also has an exact form for inverse cosh. So you'll be able to make use of that, something involving logs, to help you get an exact value in this if needed. And that is the end of the paper. Bit of a mad whistle-stop tour, and I took a little longer than the 15 minutes advertised. But what I feel like now is that if I had another hour to work at this paper, I've now looked at every question. I could skip back through and say, yeah, I feel like this vectors one will be fairly quick, and I know it's worth a bunch of marks. So maybe I skip back to that and I concentrate on that for a minute. Maybe when I get a bit bogged down and stuck, I go back to an earlier question that feels a bit more routine. So for instance, I know that there was this one. I know what to do with it. I just need to crunch through, and I reckon that's 6 marks in 6 minutes. Should be easily doable. I've got this matrices one. I've decided is going to be a little bit of a confusing bit in here, but probably worthwhile because there's a bunch of marks after that. And the fact that every question I come to I will have seen before psychologically is going to be quite valuable for me as I work through, because I won't have to do that usual bit of reading and trying to get to grips with the question and then jumping straight in. I've already done a lot of the superficial reading, look out for this, we've got 0 to 24. We already know that what this is looking for is the mean value. I've made my notes, so I can look at my notes, I can remind myself what I'm doing, and then I can get stuck in and do the maths.